All right, so we were working, let's work on letter C. F of x equals to x times arc cosine of x minus 2 times the square root of 1 minus x squared. Oh my gosh, that looks big. In this case, well, we're going to use more than one differentiation rule. Okay, can anyone name those property or those differentiation rules that we're going to be using here? Yes.
Product rule?
Product rule is one. Another rule besides the product rule?
The chain rule?
The chain rule, right? So those two rules. And of course, I mean the general power rule, which is involved in the chain rule, and the arc cos rule, you know? So, all right. So let's write down what the product rule is. So when we differentiate u times v prime, that's going to be u prime v plus v prime u. That is the derivative of the first factor times the second without differentiating it, plus the derivative of the second factor times the first one without differentiating it. Okay? So let's see. So f prime of x equals, okay, what's the derivative of the first factor? That is the derivative of 2x. So 2 times arc cosine plus the derivative of arc cosine, which going back to the table from before, okay, let me scroll this down a little bit. That's going to be formula number 2, which is essentially formula number 1 with the opposite sign. That is plus -1 over the square root of 1 minus x squared times 2x. All right? And then from here, we will differentiate the second term by itself. However, I would rewrite this the given function first, because we don't just differentiate radicals this way. So let me rewrite it as 2x arc cosine x minus 2 times 1 minus x squared to the 1/2. That way we can easily differentiate this function using the chain rule. Otherwise, with the radical form, it's not that easy. All right? So we're going to use the chain rule. So for the chain rule, so that's going to be -2 times the power goes in the front to multiply 1 minus x squared to the, subtract 1 to the exponent, that's 1/2 minus 1, that's a -1/2, times the derivative of the quantity inside of the parentheses. What's the derivative?
-2x.
-2x. So how does that chain rule work? Have you seen those nested dolls, the babushka dolls before? The one that you get one smaller every time? Well, these are Star Wars actually, and they're a little tiny, so hopefully everybody can see it. So what we do with the chain rule, so essentially we have an outermost function, right? We differentiate that function, which is the multiplication by the power. We're done with differentiating that function, and then we differentiate the innermost function, you know, which in this case, it was the 1 minus x squared. And of course, if we had more functions, and in fact there are, we just keep going and keep going. So that's pretty much the idea of the chain rule, like having multi-layer functions, if you will, you know, like just differentiate the inner and the inner and the inner until you get everything done. So in this case, we're done with this one. So let's simplify this and be careful here. Number 1. Okay, so this will be 2 arc cos of x, and plus negative, that's going to be a negative 2x over the square root of 1 minus x squared. And over here, notice how these twos cancel. And also, negative times a negative is positive. And also, at the same time, I'm going to rewrite this negative power to the denominator with positive power. That is, a we're gonna be left with this 2x in the numerator and 1 minus x squared to the 1/2. And well, of course, I'm going to rewrite this in radical form. And see how this cancels. So at the beginning, yes, this problem was getting really long, but in the end, it simplifies really nicely. Final answer. All right. Questions about this one? Of course, another very classical problem in calculus when it comes to derivatives in particular is to find the equation of the tangent line, right? And of course, and for example number 5, we will use the what's it called, the implicit differentiation, because look at the function. Can you solve for y? Well, in this case, try it. You won't be able to solve for y in this case. Trust me. So. And of course, we're given the point. We don't have to evaluate anything, so I think we're good to go. Let's just take the derivative in implicit form. So, okay, the derivative of x squared, which is 2x, plus, in this case, well, to differentiate x times arctan y, well, because we have two functions multiplying together, we will use the product rule. So, so the derivative of x, which is 1 times the second function, plus the derivative of our tangent y, which is 1 over 1 plus y squared. Be careful with the letters, with the variables, times x. And on the right-hand side of this equation, the derivative of y, which is 1, times y prime, and the derivative of negative 1, which is just 0. Right? So let's see. Let's try and simplify all this. So that's going to be 2x plus arctan y and plus x over 1 plus y squared equals, well, that's y prime dy dx. Well, so that's the derivative of this implicit function. So that's the final answer. There's really nothing else to keep simplifying. All right? Oh, wait a minute. Actually, there is. When I differentiated this y squared, that should have been a y prime over here. Right? When I differentiated the arctan, rather. I didn't multiply. So no, there's a little bit to simplify over here. So in this case, and let me, just so you don't get confused, let me stick to y prime for now. In the end, I will use the dy dx notation. Y prime. So, when it comes to implicit differentiation, we need to have all terms that contain the y prime on one side of the equation, and everything else that doesn't have any y primes, send it to the right-hand side. So, I'm going to move these two to the left-hand side first. That's going to be x y prime over 1 plus y squared equals y prime minus 2x minus arctan y. And then I'm going to move this y prime to the left-hand side with the opposite sign. That's x y prime over 1 plus y squared equals, or rather minus y prime equals negative 2x minus arctan minus arctan y. All right? And well, a couple of steps to get this done is to factor out the y prime. So that's why we move all the terms that contain the y prime in order to make it a greatest common factor, factor it out, and then divide out the remaining factors rather. So y prime times x over 1 plus y squared equals to negative 2x minus arctan y. And y, which is going to be actually minus 1. Forgot that minus 1. So what we're going to do is divide by this whole mess right here. And I know in this case, yes, at the beginning of the section, I mentioned that we need to simplify this all the way. But in this case, because I'm not really just asking you for the derivative, I'm asking for the equation of the tangent line. We don't need to simplify this. All right? So that's fine for the derivative. And so they're asking us to find the slope. And well, to find the slope, all we do is to plug in the values of x and y that we are given at the top of the page. So because evaluating the derivative, that means to find the slope. So let's go ahead and plug this in. And notation for this is very important. So let's see. Let's see what I got. Yes. Okay. So let me do it over here. So y prime evaluated at the point where x equals negative pi over 4 and y equals to 1. Okay. So wherever you see the x, plug in negative pi over 4. Wherever you see the letter y, plug in the 1. Let's go ahead and do that. So negative 2 times negative pi over 4 minus arctan of negative pi over 4 and divided by x, which is negative pi over 4, divided by 1 plus 1 squared minus 1. I know this one looks crazy, but this one will be simplified really nicely. You'll see. All right. So, okay, so negative times a negative over here, it's a positive. And 2 times pi over 4 will reduce to pi over 2. Minus arctan of negative pi over 4. Well, that in this case is, well, actually, this should have been, I was speaking only the x, so this should have been a 1, not an x, not a pi over 4. So arctan of 1 is pi over 4. And negative pi over 4 divided by 1 plus 1 squared, but 1 squared is 1, plus the other 1, that's going to give us a 2, and minus 1. And pi over 4 divided by 2, this quantity right here, pi over 4 over 2 is the same as saying pi over 4 times 1/2, which will be pi over 8. Okay? So that's pi over 2 minus pi over 4 over negative pi over 8 minus 1, but that could be a 1 over 1. You will see why. So in this case, I'm going to clear this complex fraction because this is a big fraction with smaller fractions in between, so we don't want those kind of results. I mean, you think of using the y equals mx squared 3 form with that funky number. No, we really need to simplify this one. And of course, there's a couple of ways to simplify this complex fraction. Method 1, by looking at individual numerator and denominator, or method 2, which is the one I'm going to do, which is multiply numerator and denominator by the least common denominators of every single denominator here. And in this case, well, that's the number 8. Because 8 will divide the 2 and the 4 evenly, and of course the 1. All right? So when we do that, well, so 8 times pi over 2, that's going to be 4 pi. 8 times pi over 4, that's 2 pi. And then the 8's cancel, negative pi minus 8. And that's going to be 2 pi over negative pi minus 8. And yes, I know it didn't simplify a lot, but it looked at least a lot nicer than that complex fraction. All right. So now to get the equation of the line that is tangent to a given point. So there are two elements that we need for that. What are those two elements?
You have a point and a slope.
The point and the slope. Do we have a point? Yes. Do we have the slope? Well, we just found that, right? So y minus y1 equals m times x minus x1, and that's a y minus y1, which is 1, equals m, which is this funky number, x minus negative pi over 4, all right? And well, minus minus, that turns into a plus. So y equals to 2 pi over negative pi over egg, this funky looking slope, x plus pi over 4, right? And you can just write that plus 1 over here, and you can leave it like this. That's good enough. No need to distribute it because ultimately we want this in exact form, right? Questions about? Yes.
I tried to do it when I subtracted the big one to the other side, so it was dy, when you factored out dy over x, it's 1 minus x over 1 plus y squared, but I got the same answer but negative.
But negative? I mean, no, oh yeah, you did the product rule reverse, I think? Is that what you did?
No. So when you factored out the dy over dx,
Mm-hmm.
instead of moving the smaller one over to the side of the big one, I did it the opposite way.
Mm-hmm.
But it should have given me the same one. So
Ah,
I'm not sure.
interesting. So what I did here, yes, factor the y prime, that gives me the x over 1 plus y squared, the whole thing minus 1.
Yeah, so at that step, the one below, the one right above the last one, I would have inside the parentheses 1 minus x over 1 plus y squared, and then on the opposite side, it was positive 2x plus arctan y.
Oh, okay. Oh, I see. So you got this reverse. That's the thing. So yes, I mean you should get the same answers in the end. I don't because in this case you're getting the opposite of the numerator and also the opposite of the denominator. So as long as those operations are done in the numerator, in the denominator as well, then that doesn't have to change the value from opposite to negative. So we can have a closer look at that at the end of class if that's fine. Okay. So what's next? So that's the differential calculus. Let's look at the integral calculus of this inverse trigonometric function. So let's see. What's going on here? All right. So three new formulas. Actually, you need to also memorize these ones. Actually, the one that gives us the Arctan, we're going to use it a lot throughout the semester. We're going to use it in the following section when we do this L'Hopital's rule, and we're going to use it a lot when we get to chapter 10 with infinite sequences and series. So you'll see. All right, and of course, what do we need in this case? So we're not going to look at very advanced methods yet. All we're going to do is simple U-Substitution. And so in this case, let's look at the integral and try to compare it with the formula that we have on the box at the top of the page. Well, notice in this case for letter A, we have quantity squared minus another quantity squared. The U squared usually is related for the variable part, which in this case, it looks like formula 1 is going to be the one. Now, how do we set this up for this, in order to make it look like this? So, number 1, let me take out the 2 here. And that's dx over the square root of 4 squared minus 3x squared. It's always a good idea to write it in terms of those bases squared so we can identify the u. And it happens in this case that the u is the 3x and du, which is 3 dx. And well, here is the thing. Here is where we may differ in the way that we do this, the U-substitution. Some of you might have learned the U-substitution by just multiplying and dividing by that quantity. Some of you may have learned it in a different way, which is the one I'm going to do. I'm going to solve for dx, which is 1/3 du. And then I'm going to rewrite the integral. Dx becomes 1/3 du. And that's going to be 4 squared minus u squared. And don't forget the 2 outside. And then, of course, this 1/3 times 2 outside of the integral becomes a 2/3 du over the square root of 4 squared minus u squared. And this is just ready to be integrated using the Arcane rule. That's a 2/3. Oh, come on. 2/3 of arcsine of u over a, where our u is a 3x and the a is the 4. And don't forget the plus c. Right? Let's look at another example. So the next example will involve somehow some kind of a chain rule. Oh, by the way, there's a little typo for letter B. Let me rewrite the integral instead. That shouldn't be a radical. That should be simply the integral of e to the x 4 plus e to the 2x instead. Otherwise, I think it's very repetitive to use the same arcsine formula. So let's use more than one rule in the exercise. All right. Well, in this case, what do we have? What I would look for first is the denominator. Do we have a difference of squares in the denominator? If so, that might be the Arcane rule or the arcsecant rule. But otherwise, when we have that sum of perfect squared without a radical at the same time, that's definitely the Arcane rule. For which, well, number one, let me rewrite the integral in a different way. E to the x 2 squared plus e to the x quantity squared dx, for which we can identify our u equals e to the x, and the du, which is the derivative of e to the x, but the derivative of e to the x with just an x on the exponent is simply itself, e to the x dx. And in this case, we don't need to compensate any coefficients. This is just ready to integrate. So e to the x times dx, that's our du, and that's our 2 squared plus u squared. And let's just use the form for integrating this one. 1 over 2 arctan of u over 2 plus c, where the u that's final answer. Right. So let's look at the differences between these formulas. So notice the arctan formula has a 1 over a in the coefficient, as opposed to the arcsine. Also, the arcsecant formula has that 1 over a. All right. So let's look at the next example. And yes, letter C, it's going to be a really interesting one to work with. Well, what about that one? So what do we have? The integral of 5 over 3x times the square root of x minus 4. All right, number one, we have a denominator with a variable term multiplying that radical. So that looks to me like formula number 3 is going to be the one that we're going to use. On top of that, well, there's a little issue here. That x minus 4 inside of the radical in the denominator, that doesn't look like something squared but as another something squared. You see that? But we need to have that quantity squared minus quantity squared. So we can rewrite this the following way. So there's a little trick to make this look like a difference of squares. Think of x as the square root of x quantity squared. It now looks like a difference of squares because what happens? Radical x quantity squared, the radical cancels the power, that's going to give us back to x. But there is another little issue here. So let me take the 5/3 outside of the integral dx over, okay, I'm worried about this x. Why am I worried about this x? Because, well, let me scroll to the formula again. Let's look at this formula. This should be a u squared, and the one outside should be just the u. You know? In other words, this radical x has to match this x right here, but that doesn't match, right? Well, so I'm going to use another trick right here. Okay, what's the trick here? Isn't it x just x to the first power? Well, but there's a lot of ways to write that number 1. One way, which is the one that we're going to use, is 1/2 plus 1/2. All right? And by property, by laws of exponents, whenever we have x to the n plus n, that's x times x to the n times x to the n, which is x to the 1/2 times x to the 1/2, which will be the same as saying root of x times root of x. So far, so good? Okay, so that's going to be the trick here. So that will be the square root of x times the square root of x times the square root of this ugly looking square root of x squared minus 4. Okay, but we have more than one factor. Do you notice that? We have apparently a leftover square root of x factor, which in fact it's not going to be a leftover one, because when we set u equals to the square root of x, which is x to the 1/2, du is 1/2 x to the negative 1/2 dx, which is 1/2 root of x. All right, so on the one hand, this square root of x will play the role for the u squared and the u inside and outside of the radical. And on the other hand, this other root of x right here, use a different color. Yes. This root of x right here will stand for the du part of the U-substitution that we're doing. All right, so let's see. So in this case, let me solve for dx root of x, or root of x. And that's going to be 2 du. So I'm going to replace this dx, all this right here, with simply the 2 du divided by u square root of u squared minus 4. All right, and in this case, well, what are we going to get? So number one, that's going to be 5 times 2, which is 10 thirds, and that's arcsecant of the u, which in this case is the square root of x, over a. All right, over a, which in this case is 2. But notice in this case we're also missing the 1 over a, that's 1/2. Also, another piece of information here, if you compare from the top of the page, if you compare the argument of the arcsecant function, there's an absolute value that I need to write in there. In this particular case, I'm not going to write it because think of the square root of x function. That function is never negative, right? In fact, the domain, it's only 0 and all positive values, and it outputs only positive values. So no need in this case to have those absolute value bars. But if you want to write them, that's fine. Well, never mind. So plus c, and final answer for this. So 10 over 2, that's 5 thirds. Arcsecant of the square root of x over 2 plus c. All right. I know this one it was a little bit involved. Yes, it asks us to play a little bit with our algebra skills, but I'm not going to give anything like this on the exam. Okay, so just so you know. Yeah, that one is not going to have a star. All right, let's see what's next. Oh, the next one. The next one is a very classical one, and that's actually a very common exam question. Well, so in this case, what do we have? The integral of 2 minus the square root of negative x squared minus 4x. But in this case, the quantity inside of the radical in the denominator doesn't look at all like a difference of squares. Yes, we have a square term. Yes, we have a negative sign, but the second term is a variable term. It's not a constant term, so we can call it like a difference of perfect squares. In fact, yes, even the 4 is a perfect square, but not the x. So in this case, what we need to do is completing the square. So I'm going to take that on the side. I'm going to work on this corner right here, negative x squared minus 4x. And let's complete the square for this one. So whenever we have a polynomial, a second degree polynomial with a coefficient other than 1, let's make sure that we don't have that 1. To do that, I'm going to factor out the negative x squared plus 4x, and then plus some number, some magical number that will complete the square. So what is that number and how do we find that number? To find that number, what we do is, what was that?
Half of the amount squared.
Half of the middle coefficient, or the number that multiplies x to the first power, and then square that number. So let's call it n for mysterious number. So that's 4 squared. 4 over 2 quantity squared, 4 over 2, that's a 2, and square it, that's a 4. All right. But in this case, I cannot just add a number like this, because if I do that, I would be modifying the value of this expression. So in this case, what am I doing? I'm subtracting a 4. I need to do the reverse in order to keep the integrity of the original expression. So in this case, if I subtracted a 4, what do I need to do afterwards in order to keep it the same? Add a 4, right? So now that I have this trinomial that we have inside of the parentheses gets factored the following way: x plus 2 squared plus 4. And actually, let me write it 4 minus x plus 2 squared in this one. And this is the expression that I'm going to take to the inside of the radical in the integral. All right? So the integral of 2 dx, let me take out the 2 outside. So that's the square root of 4 minus x plus 2, quantity squared, dx. And well, in this case, which form do you think it is? Is it arcsine, arctan, or the arcsec? In the meantime, u equals x plus 2, what was that again? Arcsine, right? Du equals the x grade. We don't need any compensation factors, and this will be 2 times the integral of the u of 2 squared minus u squared. That's a 2 arcsine of u over 2 plus c. And back substituting for u, that's x plus 2 over 2 plus c, right? Okay. Yeah, that for sure, something like this in which you will need to complete the square. That's a very classical exam question. So, you want to consider that? Questions about this example before moving on to the next one? All right, for the next one, what do we have? A definite integral. So, well, so in this case, we're going to use U-Substitution and also work with changing the limits to also the new limits. So let's have a look. In this case, when we have the integral of arc cosine over 1 minus x squared. So which one is going to be the u in this case? Is it going to be the x, which is inside of the radical? I mean, it looks natural from based on what we did before.
Arc cosine?
The arc cosine in this case, it's going to be the u because, well, we have basically the derivative of arc cosine, which is something that contains a radical 1 minus x squared. So let's go ahead and do that. So number one, u equals arc cos, and du equals the derivative of arc cos. Keep in mind that that one is negative, square root of 1 minus x squared dx. And in fact, that's what we have. So actually, dx over the square root of 1 minus x squared is equal to negative du. So in this case, this quantity that I'm boxing here will be replaced with negative du, and the quantity arc cosine x will be the u. And let me clean up the negatives. All right. So in this case, well, let's integrate u. Well, let's just use the general power rule. So that's a negative u squared over 2. And in this case, let's back substitute for u, which is arc cos of x, quantity squared, divided by 2. But in this case, this gets evaluated from 0 to 1/2. In this case, we're going to use the fundamental theorem of calculus, in which we will evaluate upper limit minus lower limit. And okay, let me take this negative 1/2 and do arc cos 1/2 quantity squared minus arc cos of 0 quantity squared. All right. Okay, so first of all, what's arc cosine of 1/2? If you're not sure about it, I mean, of course, you can use the unit circle. You can use the triangles. I'm going to use the triangle. So arc cosine of 1/2. So that's a 1/2. And I think this is pi over 3, isn't it? And of course, arc cosine of 0, that's going to be, I believe that's pi over 2, right? So that's negative 1/2 times pi over 3 squared minus pi over 2 squared, and that's negative 1/2 pi squared over 9 minus pi squared over 4. And of course, we can leave it like this. We don't have to keep combining these together. That's fine. That's good enough. Questions about this one? All right, so let's have a look at the next page. And this is just to wrap up the section. So let's have a look at these couple of integrals which look similar, you know. So there's only a slight difference. However, that slight difference, I mean, it's going to be a huge difference between use one method of integration or another method of integration. So let's have a look at this one. So what about letter A? Which method of integration would you use to compute this integral? The U-substitution, right? The U-substitution works whenever we have the derivative of the most complicated expression multiplying with the dx. You know, like, and when it comes to polynomials, that's typically 1 degree less than what we have for the U. So, and in this case, the U-substitution works. U equals x squared plus 9. Du equals 2x dx. And x dx equals 1/2 du. All right. So let's see. So in this case, let's substitute. 1/2 du over u, and that's a 1/2 the integral of the u over u. And what's the integral of the u over u? Ln rule, right? 1/2 ln of x squared plus 9. All right, plus c. Again, just one quick comment here. Whenever we integrate du over u, we should have written absolute value of ln of absolute value of u. But in this case, notice I didn't write those absolute values because of the nature of x squared plus 9. X squared plus 9 will always be positive, so it would be redundant to have this absolute value bar. So that's a quick comment I wanted to make, because my MATLAB might be a little bit picky on the notation. So for example, if instead we just obtain x plus 9, well, x plus 9 can output negative number. So in that case, we really need those absolute value bars, but not in this case. Let's have a look at this one. Well, this one, we don't have that factor of x to stand the du part of the problem. So in this case, we can use the Arcane Rule, x squared plus 3 squared. And this is 1/3 arctan x over 3 plus c. All right. So in this case, notice I didn't do a u sub because it's only x. But when we have something a little bit more complex, like in the other examples, it's important to show the u-du process. But not for something this simple. All right. And actually, it's fine to do this later on when we get to the methods of integration, such as, in particular, trigonometric substitution, partial fraction decomposition, in which it's fine to just go like this, without showing that UDU for simpler integers. All right, so that being said, that was the end of our inverse trigonometric functions. Let me